Can you see the diagrams, or do you have the copies that I sent? Have they been loaded there?
No, there's a problem because we already sent them the presentation this morning. They didn't have a chance to get it ready, and we don't have it here now.
So we're gonna take a use of.
We cannot see very well the.
You cannot see very well what I have on the board there, right? Or can you? Can you see this? Do you make out what the diagram has? These little bubbles there. Okay, well, let's go through that, and it's just to orient you a little bit. Basically, what it is, you see the circles there, or the bubbles, as I said. Okay, the one on top inside says bioelectric phenomena, and as you read down, this breaks into three other bubbles. The leftmost one says cell membrane potentials. The one below, immediately below bioelectric phenomena, says heart electrical phenomena, and the one to the right, immediately below, says bioelectric measurements. Okay, this is a basic orienting chart for what we have talked and what we are going to be talking. So the bioelectric phenomena include cell membrane potentials, heart electrical phenomena, and all the other bioelectric measurements. That is what this diagram says in the top four bubbles. The cell membrane potentials are of particular importance to the nerve cells, which is the bubble that connects with it on the left-hand side, and the nerve cells are the cells that produce action potentials. This is on the left-hand side, the bottom bubble. In the middle series of bubbles, the bioelectric phenomena, as we said, include heart electrical phenomena, which part of it is natural pacemaker cells. We talked about these things yesterday. And the natural pacemaker, yesterday, see, that's how close I feel to you. I think that we were together yesterday. I meant 2 weeks ago. Anyway, the natural pacemaker cells trigger the electrical sequence of the heart, and this is measurable as the ECG or EKG and the vector electrocardiogram, but we don't have to go to such depth right now. And on the right-hand side, it talks about the bioelectrical measurements with respect to the brain and the electroencephalogram, which is something we'll do long time down the line. Okay, so this is the basic framework, and we have really dispensed with all the left branch, and we are about to dispense with the middle branch of bubbles, okay? Is it understood now?
Yeah.
Okay. Now, to start talking a little bit about electricity and clear up once and for all what we do with electrocardiogram, I'll take you back to some basic physics only in terms of titles. You remember that there are four fundamental forces, as we say in physics. We are talking about the strong forces, which is the forces that exist inside the nuclei. Then we are talking about the electromagnetic forces, which is about 140 times less strong than the strong forces. And this has to do with electricity, and this is what we talk about the last 2 lectures. Then we have the weak forces and the gravity, which are something that we are not at all concerned at this point with. Okay? So out of the 4 forces, it is the second one, that the 4 fundamental forces, that gives rise to all the electrical phenomena. That's enough for physics for today. Now, matter is ordinarily, as we said, and you know that, made of atoms. And these have positively charged nuclei and negatively charged electrons. Basically, what you should remember is that the unit electric charge is the coulomb, and it is quantized in terms of chemistry, but it is something that the coulomb is made out of electrons or protons, and electrons is what runs inside the cables and the wires that we get electricity from, okay? So, we come to the concept of the electric field. I'm trying to say this physics only in terms of titles so that I orient you, because I noticed that there was a little gap last time and I really want to cover that. What is electric field? Electric field is defined as the electric force per unit charge. That is, the force a charge acts on every other charge around it. Okay? Normally, we take a test charge, as we call it, something that we call a unit, and we try to go close or go away from the measuring, from the concentration of charges we have to measure, and by measuring the force on this unit charge, we find out the field. I'll be a little bit more explicit about the field. Let me jump this, I'll come back to that. Okay. Now, the charge, or rather, let me go back to the question of the field. Anyway. Okay. The charge or the charges influence their environment around them, and especially, not especially, they influence only other charges. The force that between two charges is described by Coulomb's law. What does Coulomb's law say? It defines, we're going to see this in a second. Coulomb's law says that the electromagnetic force between two charges depends on the quantity of the charge, that is the size of the charge, and it is inversely related to the distance between them. Okay? This is called the Coulomb's law, and it obeys the inverse square law. That is, as we distance ourselves, the force among the two charges drops by the square of the distance. So, to get an idea of what 1 coulomb means, that is the basic unit of measuring charges, I'll just tell you that if you have a light bulb that is 120 watts, it consumes 1 coulomb, that is, it allows through the wires of the lamp 1 coulomb to pass in exactly 1 second. On the other hand, if you want to see the force that a coulomb of charge affects on another coulomb of charge, I have to tell you that if you separate these two charges by 1 meter apart, they will repel each other. If they are the same type of charge, they will repel each other with the force of 1,000,000 tons. So you understand how strong these forces are. So a coulomb is a very big amount of charge. And in reality, we're talking about very, very small amounts of charges that we are having inside our systems that create all the electrical phenomena. Okay? Is this a little bit better understandable in terms of the physics? I'm trying to go through the physics very fast. Does it sink in, or you have questions up to now? Are we feeling a little bit better in terms of physics?
Yes.
Okay. So, the electric force, therefore, is straightforward. It has a direction, and the direction is that of the electric field, and the force is the product of the charge times the intensity of the electric field. Okay? What is an electric field really? It is an arrangement of forces, okay? It is something like if you look at a map and you see a mountain. How do you describe a mountain on a map? You put small circles around the top that give you distance from the top on one hand and how much elevation you have. This is a field. A field is like a mountain. If you want to go against the field, it's like you're climbing a mountain, okay? In some directions, you can climb easier. For example, by putting more force for every step to raise yourself. In some other directions, it is easier to go through. Okay? Why? Because the slope is not as steep. To give you an example, okay, this is like a stair, and you have one side, or a mountain if you want to look at it that way, and on the left side you have a place where you, in order to ascend, you have to take large steps, but few steps. Or if you come on the other side, if you come from the right hand side going towards the top, you can take a lot of steps, each of which is very small. So you have to remember, you can see this diagram? Hello? You can see the diagram? Okay. So, you have to remember that no matter how difficult this step is, you are always going to have to consume the same energy in order to climb the mountain. Doesn't matter if along the way you go up or down or right or left. Whatever it takes to reach the top is always the same. And you can do it, how many steps you take is another story. You can do it in many small steps, but you can do it in one big step if you could, or in a few big steps, okay? So, as long as we understand how we climb a mountain, we should be able to understand how it is to navigate in an electric field if you were a charge, okay? Understood? Okay. So, in general, the amount you are going to do in climbing a mountain will depend just on how high you want to go, how high you want to reach. Nothing else. The same amount of height requires from you to spend the same energy. And the same thing holds for navigating into electric fields. So, I don't know if you can see this a little bit better than before, can you?
No.
Yes or no? Okay. Basically, it is a map. You are going to get all these things because I have already emailed them to you. Have you gotten the other material that I have sent to you, the other PowerPoints? Printed or something? Yes? Good. So you'll get this printed so you can read them at your ease, at your spare time. But right now, all I have to tell you that voltage, if you read this diagram, it really puts all the definitions in one place. Voltage is the specific electrical potential energy. If you read from the top to bottom, the left-hand side, you'll see that the first bubble it says voltage. And the connection says is the specific electric potential energy per unit charge, and voltage changes equals to work per unit charge against the electrical field. This is exactly what we talked up to now. So this gives you a definition of what voltage is, what a field is, and what charge is, and ties them all together. I will not go through the rest because this is, we can always come back to that. All I'll tell you is that this diagram, if you put it in your head, you don't have to worry about definitions any further. So, a change in voltage is defined, as we said already, as the work done per unit charge against the electric field. It is, as we said, like climbing a mountain. And to get back to the analogy, the difference in voltages between two positions in space is analogous when we talk about charges, okay? The voltage difference between two positions in space is analogous to the work a climber must do in order to go from one height to another height on a mountain. In other words, you can start from 5 and go to elevation 5 and go to elevation 10. You need certain amount of work, where, irrespective of whether you'll go around the mountain 3 circles before you do it, or 1 circle, or if you go in a straight line. The difference, as we said before, is the elevation, and when you approach a charge, the difference is really the quantity and the distance between the charges. Okay? So, how do we measure it? How do we measure voltages? How do we measure the differences in the force between two parts of a field? Well, we use an instrument that's called a voltmeter. And the voltmeter, in order to measure the difference in the forces acting upon your unit charge when you are in a field, you have to connect position A to position B, and then the voltmeter will tell you how much is the potential difference, as we call it, the voltage difference between these 2 points. In other words, what the voltmeter is the same thing as an elevation meter. When you go up in a mountain, you hold you hold your GPS, for example, and it tells you how high you have gone, and you can calculate from the height. You can calculate how much energy you put in. The same thing does the voltmeter in terms of the potential energy involved in a field. As we said, picture the field like a mountain that you have to climb in your head. So, like we draw maps of mountains, and we said that we are looking at a map like a number of as we say, rather not equipotential, but equal elevation lines. The same way you can look at this map. I'll go for a second and to explain this concept on the board. Can you see me here? Hi. So if you have a mountain, okay, you can describe it by taking, if this is 0 elevation, for example, if this is 0 elevation, what? You cannot see. 1 second, we'll see how we can make it better. Κατέβασε το λίγο. Κατέβασε το. Κατέβασε. 1 second, we are going to get everything right. Φέρ' το πιο κοντά ακόμα.
Yeah, perfect.
Okay, good. See, I think of you. Okay, this is 0 elevation down here, correct? Okay, if we go 1 elevation higher, we'll call this elevation 1. And then elevation 2. Okay? And then elevation 3. We can cut the mountain, in other words, in our minds, in different elevations. Okay. And then we can take those elevations. Μπορείς να κατεβείς λίγο κάτω. Αλλιώς. Ανέβα. Δεν πάει άλλο. Κι άλλο κάτω, έτσι. Ναι, εκεί. Now, if you take these elevations, and if this is the base of the mountain, when you look at it from the top, Okay? If this is the base of the mountain, this is the zero elevation, then you have another elevation that may go like this, which is elevation 1, and then you have another elevation, which is elevation 2, and then you have the other elevation here, which is elevation 3, elevation 4, and finally you reach the top, which is elevation 5. This means that from each elevation to the other is the same amount. Κατέβασε λίγο κάτω. Κατέβασε κάτω. Αλλιώς, πάνω τότε. Good. Okay? For every step you take here, we assume that these are equal elevation, equal distances. You have one ring inside this kind of a map. So you can use these maps. They use them all the time in order to describe physical features, the same way we use in order to describe an electrical field. Okay? Is this understood? Have you seen maps like this before? Yes? Okay. So we are coming back to our diagram here, and we can say that we can describe the same way that we describe the height of a mountain, we can describe the strength of the field in terms of equipotential lines. That is, lines that have the same voltage. Potential equals voltage, okay? So we can make contour maps, as they call them, on any body that includes some kind of on the surface of a body that includes some kind of a charge inside. So in effect, if we want to describe a charge and its effect, we just have to follow the equipotential lines. Now there is a law which I just want you to remember only its name. Don't ever try to see these things any further. This law is called Gauss's law. And what it says is that the potential lines, the lines along which we measure the potential that cross a surface is always equal to the charge enclosed inside. Basically what we are saying is that if you have charge in one space, in one part of the space, it is going to influence the area around it. The more charge you have, the more potential lines are going to go towards the surface and out. But if you have zero charge inside, then nothing will go out, okay? Now this is important to us. Why? Because it is important to us because if you recall last time, and this is a diagram that we tried to draw on the board last time, okay? If you look at this diagram, what I have done is take a dipole that is two charges, a positive and a negative charge, and put them inside a body. And you can see that in each part of the body there is going to be a different potential. Why? Because each positive and each negative is at a different distance. And if you recall the law that we had described before, then it tells you that at each part of the surface it is going to have different potential, and in fact we can measure this potential with some arrangement like this. Okay? It is the same thing that you have seen before, only this time I have drawn on the surface the isopotential lines like we did on the mountain. Okay? You see a dipole inside, and you see that I use a voltmeter to measure the difference in potential between any 2 points on top of the surface. Well, that's more or less what we do when we try to do the ECG, the EKG. Yes, go ahead, tell me.
If you zoom in on the picture, we don't see all the details.
You don't see all the detail, we'll come back. Γύρισε πίσω, γύρισε να δει. Γύρισε, κατέβασε, ναι, κάνε το zoom. We'll zoom on it for a minute. Και διόρθωσε και το αυτό.
What's that, the minus and the plus?
Is it better now? Focus. Let's, από πάνω με το φακό. Let's try to focus it a little bit better. Is this okay now?
Yeah.
Okay, what basically have in front of us is the idea that we have two charges separated inside a body. They reflect their presence by imposing isopotential lines on top of the surface, and if we take a voltmeter between 2 points on the surface, we are going to see a potential difference. It is the same thing as the example that I gave you about climbing the mountain. Are we clear up to now? Good. No, I mean, this time I'm going to go slow, but I really want to finish with everything about the EKG. So, do you have time to jot this down? Can I go on? Good. Doesn't matter. Now, a corollary of Gauss's law is that the area integral, don't panic with the physics. I made it a point today to give it to you as simple as possible. The area integral of the electric field over any closed surface, and by that we mean by analogy the energy we'll spend by taking a hike on the mountain and returning to the same starting point, this is what an area integral means, is equal to the net charge enclosed in the surface divided by the permittivity of the space. That is, if we walk through, if we go around the mountain, if we climb up and down and return to the same point, you're going to spend some energy that it will have to do with the steepness, let's say, of the mountain. Okay? So, in general, since we talked about charges, we can say that an isolated charge, we can call it as a monopole. If we have positive and negative charges placed close to each other like what we had before, this is a dipole. Two dipoles give us a quadrupole, and so on. You can do this forever, but we're not interested in this. What we are interested in is that dipoles are significant, have a significant application because they allow us to interpret cardiac and brain activity. And it is cardiac activity that we are concerned with today, so this is why we are talking about dipoles. So, coming back to the contour maps that we had, the electric field of an electric dipole can be constructed as a vector sum of the point charge fields of two different charges. That is, you take the two different charges, you put them side by side, and we connect their lines, their isopotential lines, and we can come up with how a dipole will look. That is how the isopotential lines of the dipole will look. And this is the mathematics of it, which you don't have to remember. You are going to get this with your notes, but please do not learn it. Just remember that it exists. And basically what it says is that the potential of the electric dipole is found by superimposing the point charge potentials of the two charges. That is, if we take two monopoles, we can make a dipole. Two different charges, and we can see what they do in the space around them, then they add at every point. This is what this means. So, I come back to the cardiac function lecture of last time to remind you of what we said we were going to talk. And at that time we talked that we were going to explore the concept of the electrical dipole. And this is the last time you're going to hear from me trying to explain it. I think that by now you have cleared it up enough in your mind to be able to go on. And we said last time of why is the electrical activity of myocardial cells modeled by a dipole. And this is when, maybe because you're too tired last time, we had a long, long day, and it was the first time that we did the lecture this way. That's when you started really losing me, and this is why we stopped going through the lecture last time. But the electrical activity indeed of myocardial cells indeed can be modeled by a dipole, and I will bring back this old slide for you. I presume that you have it already there. It is from the old slides. You have seen that last time, where I had drawn on two connected cells, heart cells. Remember that we said that the heart cells connect through intercalated discs. You remember that, I take it, right? Yes? I see you waving your heads. So, when we have an excitation in any one of those cells, the electrical lines, and now you have seen plenty of electrical lines today, cross to the border, cross the border, and then they go to the next cell, and this is how the excitation moves down the membrane from one excited part to the non-excited part. You recall all that from, and by now you should have read it in your books also, so I think you should be clear about it, correct? Yes, all of you agree with me? You're awfully quiet today. What's happening? Oh. Okay, no, really, I mean, I really need some feedback at this point. Are these concepts clear by now?
Yes.
All of you, okay. So, remember that last time I also put this slide up that had three instances of the excitation moving down a cell. Correct? Yes. And I had told you that you can analyze the activity in terms of local small dipoles. You recall that? So basically, when the activity is near the beginning of the cell, you have one small dipole looking to the left in this picture and a larger dipole looking to the right. Why? Because you have more charges on one side than on the other, in each case. And the two add up to give one final dipole that represents this cell, which is the one on top, with a little bit darker color. You recall that from last time, yes?
Why there is a dipole in on the top right cell? Isn't the dipole cancel each other?
Yes, but they're not the same size. You are right. But they are not the same size, therefore the net is on top. You have two dipoles. You see the blue line going down in the middle of the excitation area?
Yeah.
Okay. You have a small dipole looking to the left because you have very few charges on the left compared to the excitation area. All right?
Okay.
And then you have a lot more charges on the other side. So you have two dipoles, one that represents half of the cell, or not half of the cell, but the part of the cell that is to the left of the blue line. And then you have another one which represents the activity of the cell to the right of the blue line, correct? The total activity is summed up on top. The small part cancels part of the big dipole, and this is the remaining, correct? And as the excitation goes down the cell, you see that these things become almost equal, and the net becomes very small, or zero at some point. And then as this thing continues, you have the inverse situation, which is down to the left side, the bottom left picture. Is it understood now?
Yeah, but isn't there a point in a cell where both dipoles are equal and opposite?
Absolutely. Absolutely. It will be another picture that actually we should insert between the second picture and the third. That is, between the top right picture and the bottom left picture. There should be another one where they will exactly match each other, and there will be zero. But in drawing those diagrams, I skipped over this. This way I had the question coming. Very good. Thanks for paying attention. This is something you pay attention at. Okay. Are we all clear now about dipoles and cells? Okay. Now, you'll be wondering what 3 times 1 means, okay? This is to remind me to put some of my drawings on the board. Όχι, όχι, ας την κάτω αυτό. Ή βάλτε, δεν πειράζει. Okay. Δεν πειράζει. So, what you see here is I take one cell like the one that I drew before, right? And I put it inside the body, and like the picture that I had shown you earlier, you see here how the charges on this cell influence the surface of the body, okay? It is not very well drawn, but excuse me, but this is the best I could do, okay? Now, okay, and here is the same picture, a little bit more stylized. Now we have taken the actual picture of the cell, and we have put that's good, an arrow representing the dipole inside the body, and you can see how it impresses equipotential lines on top of the surface of the body, and how we can measure different voltages depending on where we are looking at. You see, you have 3 voltmeters there that I have placed around the body, and I just want you to pay a little bit of attention to see the top first. And you see that the electrodes of the top voltmeter are attached to the same region in terms of equipotential surfaces, right? You can see that? Therefore, this thing you should not see any difference, and indeed the little voltmeter that we have on top is at 0, okay? But if you take either on the left side or on the right side the voltmeter and you put it between different isopotential surfaces, you'll see that they are going to measure the difference between these two surfaces. Can you see it? Can you see it or not? I mean, when I say see it, I mean, can you understand what I'm trying to tell you, this diagram?
Yeah.
Okay. Now, depending on how you put your electrodes, what you call the positive or the negative electrode, the arrow inside, the pointing is going to be different. In one case it points towards the negative part, and the other points towards the positive side. Okay? But the two right and left voltmeters, they show maximum in both cases because they represent potential differences. While in the first case, we are measuring inside the same potential area, therefore we couldn't see any difference. Now, There is another. Can I remove this? Have you jotted it down?
No.
Okay, I'll wait. It gives me time to take a sip of coffee. You see, I'm relaxing here.
Why the top one and the left one are posted are directed from the minus to the plus?
Excuse me. I'm sorry, there was some noise on your part. Tell me, what is the question? Why the top one?
Top one and the left one are from minus to plus, like the dipole showed.
Okay, let me. The plus or minus refers to the electrode that you use in order to, or the probe, let's say, okay, that you use to touch the body. You have to define which is positive and which is negative. There is no way to know that. There is no negative and positive, something we decide, right? Nature only knows that there are two different things. We call one positive, we call the other negative, right? So we assign in our voltmeter what is the positive probe and what is the negative probe. And then depending on how we stick it on the body, we are going to see the voltmeter show us. That is, this is the difference between the left voltmeter and the right voltmeter. You see that they have different polarities, as we say. Wait a minute, I may have done something wrong here. Negative, positive. Who asked this question? Who asked this question, really? Congratulations. The arrow should be reversed on the other side. One of the two side arrows should be reversed. You understand me? In other words, this arrow or this arrow, depending what you want, is wrong. Actually, this one here should be this way. Okay? Are we clear now?
Yes.
Because the potential is the same between here and there. In other words, between here and here is the same potential, and between here and here is the same potential. Therefore, they should both show the same difference. And you're right. Now, why is it looking downwards instead of upwards? Because we put on what is the positive side of the dipole, the negative probe of our voltmeter. So it's going to show a reverse. Correct? Are we clear? Thank you for this question. If I had staged it, it would not have come better. Okay. Αλλιώς. Now, όχι. Αλλιώς. Έτσι. Okay. Can you see this diagram? Can we correct this one? Do we need to correct this one? Okay. Over here, okay, it should point to 0, and it is because they both are looking at this isopotential area. Okay, so there shouldn't be any difference. So it should look at 0. Between here and there, this is positive, this is negative. So how should it look? It should point maximum, and let's assume that this is the positive side, right? And over here down below, it should also point to 0 because it goes between two areas that are between the same parallels, that is isopotential area. So the potential here and the potential there is the same, therefore there shouldn't be any potential difference. And it should point to 0. This is correct. Do we agree?
Yes.
Okay. τήρησε σήμερα.
Εξετάσεις στην παρουσίαση.
Στην παρουσίαση. Okay. Now, a minute ago we talked about the principle of superposition. Once more I'm going to come back to this and tell you that there in mathematics there are ways you can take two arrows, two vectors, if you want to call it, or two dipoles, doesn't matter, and add them together. And you can continue this many, many times depending on how many arrows you have. This is from last lecture, this picture here. So you already have seen it, but I'm going through this so that we clear up things. So, in the body, as I said, we have millions and millions of cells. The heart, I will give you a number, don't take it literally, but it is an order of magnitude. The heart has something like 10 billion cells, that is 10 to the power of 9 cells. Interestingly enough, it has about as many cells as the brain does neuronal cells. It is very interesting that these two organs have about the same amount of active cells. So, each cell at each instant in its life, every moment that is, it can be represented by a dipole. Sometimes a big dipole, sometimes a small dipole, depending on how active it is. But at every instant, every cell is represented by a dipole on the heart. And using mathematics, one can easily add all these dipoles, and in effect, that is what happens in our body, because if we are going to take one probe or 1 voltmeter, and it's 2 probes, and we put it on the outside of our body, what we are going to read is not the dipole of each cell, but we're going to read the effect of the sum of all the dipoles inside the body. And since in the torso it is basically the heart that is giving dipoles continuously, that is producing electrical dipoles continuously, so it is the activity of the heart that we're going to measure if we put electrodes on the outside of our body. Is that understood? No answer?
Yes.
Yes? Okay. Can I ask you a question?
Yes.
Okay. The moment your heart, you remember last week's lecture when we talked about the parts of the heart that get excited in a different order, correct?
Yeah.
Okay. When the atria get excited, all right? Where do you think most of the big dipoles are going to be in the heart?
Where?
I say when the heart gets excited, right? And the atria get excited. This is the first part of the heart that gets excited. Remember we talked about the cardiac cycle in terms of excitation last time? Okay. The atria get excited first. So at that instant, where do you think most of the large electrical dipoles are going to be in the heart? Over?
Toward AV node.
AV node, you said? Okay. Let me... you are basically correct in terms of location. It will be between SA node and AV node. All the tissue there will be excited. This is the first tissue that gets excited. So the myocardial wall, not only the AV node and the SA node, but all the myocardium of the atria is going to be active, right? In the first 70 milliseconds we said, right? Remember? So the moment all these are active, this is where most of the big dipoles are going to be. So the resultant dipole, the one that we saw, will represent activity of the atria. And when down the line the ventricles get excited, then the activity, the resulting dipole, is going to represent the dipoles that are excited, or the dipoles that are produced by the cells of the myocardial wall of the ventricles. Therefore, at different instances around the cycle of the heart, we're going to see different representation of the activity. The activity we're going to measure on our body is going to be representing different things. Is that understood? Okay. All right. So, now, at this point, I'm going to come back to what I told you about Eindhoven. You recall Eindhoven? I told you that Eindhoven was a Dutch physicist, physician, and whatever else who invented the electrocardiogram. Okay? Well, what Eindhoven realized was that because the limbs of our body are long and thin compared to our torso, no currents or no significant currents were going to be lost going towards that way. So he basically came to the conclusion that if you put an electrode on the wrist, or an electrode near your, if you put an electrode on your wrist, or an electrode up near your arm or your armpit, it wouldn't make any difference when you measure what is happening inside your torso. They would show approximately the same thing. If you recall last time, I put on the board a map of a person which I had done a small diagram of. Let me do it again. Okay. I'm sorry I'm exaggerating so much, but if you have the heart in the middle of the body, okay, then the film lines that it produces with its activity are not going to be lost so much going here. So basically, if you measure here, or you measure here, or you measure there, or you measure over here, it is going to be approximately the same. But if you measure here and you measure there, these between them may have much more, so much more differences than between here and there. Okay? This is because of the shape of the body. So, I'll go back to what I did last time now. Which was to draw a person very stylistically and put over here the heart. Okay? And if you recall, I said that if we put electrodes here and here and here, that in effect electrically the distance like this is the same. So this led Eindhoven to the diagram that I'm just going to draw, which is to consider that these things represented, if you raise your hand, these things represented an equilateral triangle. Okay? Have you seen this? Are we straight with this now?
Yeah, but what's the same, George? I didn't understand. What's the same between up and down, between the hand and the...
All I said is electrically, in other words, if you take two probes, we said that if you put a probe here or here, it's not going to make much difference, correct? And if you put the probe here or here at the shoulder, it's not going to make much difference either. So basically, from here to the heart or from here to the heart, electrically was about the same resistance. Let's call it that way. This is an oversimplification, but it is going to make things clear in your mind. Remember, this is an oversimplification. Okay? So, we agree on that? Hello?
Yeah, we're not talking about electrical potential there, right?
No, no.
Just talking about...
we're talking about how much. We're not talking about electrical potential. We're saying that the resistance, that is how much you're going to diminish your signal from here to there, is not going to matter so much. Okay?
Okay.
So, now we come to what you said about potential, because this is the important part. What we are saying is that the body, which will have different potential lines on top of it, like we drew before, okay? There are points on it that can be connected together to form an equilateral triangle. Actually, this is not very good. Let me